My name is Ray Volkers. I'm the head of the School of Physics at the University of Melbourne, and it's my great pleasure today to introduce today's July lecturer, Harry Quiney. So Harry has an MSc from Monash University in Theoretical Chemistry, and then he moved to the UK to do a DPhil at Oxford in Theoretical Atomic and Molecular Physics. He then spent 20 years in total at Oxford, first as a research fellow for the Royal Commission for the exhibition of 1851, if you know what that is, and it's a famous scholarship to go to Oxford, and then as a lecturer in physical chemistry and mathematics at Wadham College. He then returned to Australia, and in recent times he led the theory and modelling group of the Australian Research Council Centre of Excellence for Coherent X-ray Science, which was led out of our department, and he was appointed to the School of Physics on a permanent basis in 2011, where he is an associate professor and reader. So he is a member of the Theoretical Condensed Matter Physics group in the School of Physics, and is now leading actually a new group in a new Australian Research Council Centre of Excellence, which is devoted to advanced molecular imaging. And this centre is interdisciplinary in nature, and it is doing research on science which spans physics and biology in particular. So this lecture is very appropriate because this year is the UNESCO International Year of Crystallography. And today Harry will survey the history of crystallography and the role it has played in the development of materials science and molecular biology. Harry.
Okay, thank you, Ray, for that introduction. Thank you all for coming out on this rather breezy and chilly July evening. Today's lecture will be about crystallography, and the title is "To See a World in a Grain of Sand, a Century of Crystallography." To be strictly speaking, it's actually a century of X-ray crystallography, but the discussion will be more far-ranging, and I'll look at the far history of the subject. As Ray said, the work I do in the school, it's in theoretical condensed matter physics. It's been for a long time with CXS, and more recently it's with this new centre which undertakes research into areas which are at the border between physics and chemistry and biology and computational modelling. Now, the origin of the title of the talk, To See a World in a Grain of Sand, is the poem by Blake. To see a world in a grain of sand and a heaven in a wildflower, to hold infinity in the palm of your hand and eternity in an hour. It's tremendously inspiring. It seems to the modern ear, it sounds about the atomic world. It's about space and time and beauty and fractals and biology, and yet it's really about none of those things as far as Blake is concerned. Blake was a mystic. He's very difficult to pin down. He was an artist, and many of you no doubt have been to the National Gallery in Victoria in St Kilda Road and seen the exhibition of Blake's etchings, mainly of the Book of Job. They're fantastic. I'm a huge fan of Blake. But Blake was not a scientist. This is Blake's rendition of Newton. It's a famous picture. Newton naked and alone and in his own world, divorced from nature, not noticing the nature around it, just taking measurements of stuff. Blake was an implacable opponent of the English Enlightenment. He saw science as dead and a withering aspect of human activity. It's not obvious to me that Blake knew many scientists. If he knew any at all, if he knew any, they couldn't have been much good, or I'm allowed to say they came from Cambridge. And he's famous for having said, "Art is the tree of life, science is the tree of death." So it's not a particularly auspicious start, but nevertheless I still like the quotation, "To see a world in a grain of sand." And I like it because of this. This is an image of a collection of microcrystals of influenza neuraminidase. Now, influenza neuraminidase is an enzyme which exists on the outside surface of the influenza virus. And it's actually largely responsible for the reproduction of the influenza virus when it infects a host. And if one could actually somehow nobble that reproductive process, one could stamp out the reproduction of influenza when it infects the host and actually stop the spread of flu across the world. Now, there's been many outbreaks of influenza over the years, and the 1919 pandemic is, of course, very famous. It wiped out more people than World War I, and in terms of death and mortality, is to be feared more than war, really. And every now and again, there are fears that it will spread through the human population. In this particular case, it was isolated from noddy terns up on the Great Barrier Reef and their migration. And the fear is that they would bring this influenza virus or mutation of avian flu. It would enter the human population and wipe out, literally decimate the population. And the crystals themselves are beautiful. These are crystals of an enzyme which grows on the outside, or is attached to the outside surface of the influenza virus, extracted from egg white. Actually, the flu is grown in egg white, extracted, purified, and crystallized into these rather exquisite little forms. It's even been done in space. These little microcrystals here were grown in space in an attempt to grow more perfect, morphologically regular crystals for the purpose of getting better and more perfect crystal structures, or being able to get signals out to higher resolution. And this is a collection of what these crystals look like. They're proteins and viruses, all grown in space and all adopting these rather exquisite, multifaceted forms. And this is a world at a grain of sand. This is the world of the macromolecules which make up life on Earth. So an overview of the talk, I'm going to discuss crystals and symmetry and the far history of the subject. I will then enter a celebration, the centenary anniversary of Bragg and Bragg, and X-ray crystallography and how that came about. We'll look at the fundamentals of diffraction physics, and I have a little demonstration here with a little audience participation to spice things up. And then we'll look at some new things, quasi-crystals, crystals which are not formed in the way that it was believed crystals are formed for many a long year. We'll then look at how interdisciplinary work in physics and biology is striving towards solving new problems, frontier problems in human health. And finally, we'll look at the far frontier of diffraction from nanocrystals, so crystals much smaller than those tiny grains of sand, and possibly even single molecules, no crystals at all, in order to determine molecular structure. So we'll begin at the beginning, and we'll begin where I gave a talk last year, and this is where we began last year, but there will be a bifurcation point. 100 years ago, the Australian government invested the princely sum of £15,000, which is a lot of money in those days, to host a meeting in Australia. And this meeting had leading scientists who went to Adelaide and Melbourne and Sydney and New Zealand. There's a 1,000-page document which records a snapshot of what science was like 100 years ago today. It was 100 years ago, not quite today, but 100 years ago. The delegation was led by Ernest Rutherford, and the cutting-edge physics of the day, the things which are under discussion, was atomic structure and atomic physics, the Rutherford atom, Bohr theory, Moseley's X-ray survey of the elements, which is what I talked about last year, and Bragg diffraction. And 100 years ago, in the School of Physics, it was then called the School of Natural Philosophy, over in the place which is now called Old Physics, on a Tuesday, on the 18th of August, which is my friend's birthday, Sir Ernest Rutherford said, "We now have two powerful methods that aid us in determining the inner structure of the atom, the scattering of high-speed particles in transit through matter and the vibrations of the interior parts of the atom. And in modern language, this is something we teach undergraduates now as a routine part of physics. Scattering and the structure of matter includes Bragg diffraction, and scattering from periodic solids, and in its inelastic form actually is the basis of particle physics, and spectroscopy, the electronic structure of atoms, how the electrons are arranged in shells around nuclei, which give rise to chemistry. And with one qualification for what was being discussed in 1914, this study of solids and atoms is as true today as it was 100 years ago. And the qualification is the word periodic, which we'll come to a little later on. Now, it seems that the discussion 100 years ago was rather robust, and there were both chemists and physicists and a few biologists and geologists there, and one Professor Henry Armstrong, who was professor of chemistry at City and Guilds College in London, said, "The arguments used here are so novel, so daring, the contentions so original, that at present they, the chemists, are not in a position to appreciate them, still less to criticise them effectively," which I think is shorthand for he didn't really understand it. Physicists, unfortunately, in the past, have held aloof from chemists. Sure. And the movement now in progress is therefore to be welcomed. He's welcoming this interdisciplinary interaction between physicists and chemists, hence the value of the present discussions. Now, in preparing this talk, I found further musings of Professor Henry Armstrong, who later became professor at a more august institution, which is University College London. And 13 years later, he seems to have given up on this whole physics and chemistry business in response to an article by Bragg, where he discussed how he determined the structure of common salt. Bragg asserts that in sodium chloride there appear to be no molecules represented by sodium chloride. It's arrived at by some chessboard pattern, not the pairing of atoms. He had preconceptions. He had very fixed views on what sodium chloride was supposed to look like, and sodium chloride was supposed to be made out of molecules. This statement is absurd to the nth degree, he said. This is not chemical cricket. It were time that chemists took charge of chemistry once more and protected neophytes from the worship of false gods, by which he means us. So what is crystallography? Since 1914, crystallography has examined the arrangement of atoms in crystals. And since 1914 in Bragg, which we'll get to in a moment, it's been all about determining how the atoms are arranged in space. Before that, crystallography was really the study of the macroscopic geometry of crystals or the morphology of crystals, and these days you'd call it mineralogy. Before 1982, a crystal was regarded as being a solid constructed from a spatially periodic arrangement. So there were certain elementary units which were repeated in space by translation in three directions, a periodic solid. But after 1982, there was a major groundbreaking discovery, which they found solids which were able to on which you were able to perform Bragg diffraction, which were not produced by the simple periodic arrangement of elementary subunits. And so the International Union of Crystallography subsequently redefined the crystal, the term crystal. So crystal now has a different definition than perhaps the one you learned at school in terms of planes and periodic structures, to include both these ordinary periodic crystals and so-called quasi-crystals that we'll discuss a little later on. So that anything is a crystal if it produces Bragg diffraction, and we'll discuss what Bragg diffraction is in a moment. So there have been these major changes: mineralogy to the study of periodic solids, to expanding that to the study of quasi-periodic solids, which are ordered but not strictly periodic. And here, for today's talk, I'll only really consider X-rays to determine electronic structure, atomic structure, simply because this is the 100th anniversary of X-ray crystallography. But in fairness to many of my colleagues, I should point out that electrons and neutrons are also used because if you throw them fast enough at a system, they possess short wavelengths. The physical principles of electron and neutron diffraction are essentially the same as the physical principles of X-ray diffraction, and as Ray mentioned, this is the UNESCO International Year of Crystallography, and the reason that we're here to celebrate that anniversary this evening. So to begin at the beginning, crystals and symmetry. The earliest serious discussion I could find of the importance of symmetry in the structure of crystals was actually by Johannes Kepler, who's better known to most of us for his work on astrophysics and orbital motion. He was the court scientist for the Holy Roman Empire, and it was his job to make and publish scientific observations. And in 1611, he made a small scientific observation, a small gift of mathematics to His Imperial Majesty King Rudolph II, Emperor of the Holy Roman Empire, in which he discusses a New Year's gift of hexagonal snow. And in it, I was surprised to discover is this fabulous drawing. Now, it doesn't look much perhaps to you, but this drawing appears in pretty much every modern textbook of crystallography. This is long before people knew about atoms or even suspected, and Kepler at no point apparently makes an atomic hypothesis. What he does say is that it seems that crystals are constructed from smaller units and that the way that they're packed together is somehow, or could somehow be reflected in the morphology of visible objects. And so he speculated that the six-sided shape of ice crystals in snowflakes was in some way related to a hexagonal packing of spheres. That's a 9.5 out of 10 for being right 300 and a bit years before the discovery of the atom. Robert Hooke also made copious observations about ice crystals, and in his famous coffee table book, Micrographia, published sketches of six-sided objects which he'd plucked from the snow outside, and he observed that they all had this six-fold symmetry, but they all seemed to be unique. And so this is captured for all time, a dozen or so snowflakes observed by Hooke with his optical microscope. Now, the first real contribution to mineralogy and to what we normally think of as crystals was made by Nicholas Steno in the 1660s, 1670. Steno made significant contributions to paleontology and geology and stratigraphy and also crystallography. So those of you who enjoy watching Time Team and the way that they burrow through the layers to tell you what particular moment in time a particular event occurred, you can thank Nicholas Steno for being the first to make an identification between the layered structures one finds in the ground and the time at which they were laid down. He left science and entered the Catholic Church and was beatified by Pope John Paul II, so he's a fairly major figure in the Catholic Church. But before he did that, he laid down Steno's law, which is that the angles between corresponding faces of mineral samples are the same for all specimens. So if I were to have two pieces of quartz, one that I picked up in France and one that I picked up in Prussia, and I cleave it and I look at the faces and the angles at which the faces meet, then if they're both quartz, then they'll both have the same angles of meeting. And this became known as the first law of crystallography. And this was all written down in his book, which was published in 1699. Now, the man who's largely credited as being the father of modern crystallography is René Justuy, who accidentally dropped a specimen of calcite. And it wasn't even his specimen, it was a friend's. But he dropped it on the ground and it broke into a large number of small pieces. And when he looked at the pieces, each of the pieces was self-similar in the sense that it cleaved into trigonal or cubic or extended cubic structures. And if he further broke them, it always broke with the angles being the same on each of the faces. And then he postulated that this was because they were somehow made of elementary units, and these elementary units were repeated in space, and that by cleaving the samples and the shattered pieces, one was merely breaking it down into its elementary units. It's said that when he dropped the calcite crystal and saw the pieces scattered on the ground, he said, "Tout est trouvé," everything is revealed. The first serious mathematical discussion of the symmetry underlying crystals was made by Auguste Bravais. There were earlier attempts to do this, but Bravais was the first one to get it right. He identified the 14 unique geometrical structures that one can use to produce an infinite three-dimensional lattice simply by translation in three directions, which I've labelled here as A1, A2, and A3. So if I get these elementary objects and I move it by n units in A1 and n1 units in A1 and n2 units in A2 and n3 units in A3, I can build up a three-dimensional crystal which is infinitely periodic. That is, it repeats itself with regular periods. And for example, one of the simplest ones is a cubic lattice in which I've got an atom or a molecule or some object placed at the vertices of a cube, and the same object placed in the geometrical center of the cube, and then I can produce an infinite three-dimensional lattice simply by repeating that pattern over and over again, stacking them to the left and to the right and up and down, and forward and backwards. And these are the 14 Bravais lattices. They fall into 7 general categories: cubic, tetragonal, hexagonal, orthorhombic, rhombohedral, monoclinic, and triclinic. And you can see that the cubical structures also fall into subgroups: face-centered cubic, which has an atom actually in the faces of the cube; body-centered cubic, which is the one I showed you before with an atom in the middle; simple cubic with atoms only in the corners, and so on. And that's all there is. There are no other possibilities for producing infinite arrays of regular structures. Also, at around the same time in the field of mineralogy, and long before there was knowledge of atoms, was William Miller. William Miller was a Welsh mineralogist, and he devised a scheme to be able to classify the faces that occur in crystals by looking at the intersection of planes inside these building blocks, these Bravais lattices. And what he did was he specified a particular direction which was perpendicular to these planes, and if you specify the direction of the vector, then any plane which is perpendicular to that vector lies in one of the symmetry planes of the Bravais lattice. And the system that Miller devised, well, 100 or going on for 200 years, more or less, is still in use today and is still the standard means of classification for crystalline objects. And here is an example of the ways that one can draw these planes in cubical structures and the labeling schemes that go with it. Now, it doesn't matter if you don't follow the details of that. It suffices to say that there are 14 basic structures. The basic structures are subdivided by planes which subtend corners and faces and edges, and that there's a labeling scheme that allows us to identify which plane we're talking about. And then on top of all of that, the final wrinkle in all of this, we have our Bravais lattices, we have a labeling scheme for the planes within the Bravais lattices. What we then need is a scheme to represent symmetry operations, rotations, reflections, inversions of the objects which make up the molecule. Now, it turns out that there are only 32 possible sets of operations that one can construct, the so-called 32 point groups, which represent transformations under reflections, rotations, inversions, improper rotations, and the identity operator, which is a nicety we need not go into. The 14 Bravais lattices and symmetries which are specific to solids, which involve a combination between translation and rotation, which represents a helix or a screw. Crystals actually have screw locations or screw symmetries such that the planes actually look like a spiral staircase. So that's a symmetry that has to be built in, as well as a glide plane, which is a symmetry of a translation along one of the symmetry planes of the lattice. And if you put all of that together and you argue about it for about 30 years, because there was about 30 years of argument about exactly how many combinations of these things there were, it turns out, and there's general agreement, there was general agreement more than 100 years ago, that there are 230 possible combinations of the Bravais lattices, the point group symmetries, and the symmetries which are intrinsic to continuous solids. And that's it. There are only 230 ways that you can build your solid. And of those, 219 are absolutely unique. And then there are, whatever it is, 11, which are related as chiral partners, so left-handed and right-handed mirror symmetries. And that's it. That is everything that there is known about the symmetries of solids. and it was known in 1892, and it was determined by Fedorov and Schoenflies. And these symmetries, the 230 space group symmetries, are often known as Fedorov symmetries or Schoenflies symmetries, depending on which side of the Iron Curtain you're brought up in. Which brings us to mineralogy. Now, this is an entirely personal thing, because this is a rock crystal that was given to me by my great uncle when I was about 8, which I kept all these years. It turns out that my mother's family were Cornish tin miners that came out here in the 19th century. And my uncle Bill was a gold miner, and he had a large collection of these things on his mantelpiece, and I went to see him one day when I was 8, and he gave this to me, and I've kept it ever since. And it's rather nice that I can bring it out in a moment like this and actually make some scientific use of it, because this is a rather splendid example of an ideal quartz crystal. Now, an ideal quartz crystal, as I have in my hand here, and you can see on the screen there, terminates in 6 triangular faces, and you can see one of the triangular faces pointing up at the end there. Uncle Bill apparently hacked the other end of this off with a chisel or something and smashed it. It's actually very rare to get crystals that are hexagonal and pyramidal at both ends, but it is possible. The chemical structure of this mineral is silicon dioxide, and each silicon atom is surrounded by 4 oxygen atoms, and each oxygen atom bridges to silicon atoms, and there's a unique packing which is reflected in the morphology of this huge crystal. And if we look even more closely, as I did this morning and took a photograph, you can see that although the face feels incredibly smooth to the touch, the light reflecting off the surface actually reveals the way that the face was formed by building up around screw dislocations, and you can see some of the screw dislocations actually on the surface. So that the surface is not actually built layer by layer. It actually builds up from an error or a misreading of the pattern around and around and around in a circle until it fills up the face, in which there's still a screw dislocation which builds up the next phase and the next phase. So contrary to what you might believe, or certainly contrary to what's taught in a lot of textbooks, the presence of these small dislocations is actually crucial for the growing of large crystals like this, simply because the energetics of laying down one crystal plane after another in perfect symmetry is actually thermodynamically disfavored. And this is the structure of silicon dioxide. Which brings us to the Braggs and the start of our 100 years celebration. Well, on the left is William Bragg, and on the right is Lawrence Bragg. Poor Lawrence Bragg is the victim of a Victorian and Edwardian habit of naming the first son after the father. Social handicap I share with my father and his father before him. And most of the information in this is taken from a recent biography by John Jenkins, William and Lawrence Bragg, father and son, the most extraordinary collaboration in science. Such was the fame of Bragg and Bragg that their images, and exactly the same images, were recorded on postage stamps all around the world. This, I believe, was to celebrate the 50th anniversary of the awarding of the Nobel Prize. So, I don't want to go into the whole history. You can read the book. It's a very extensive document. In terms of the Australian context, the Bragg family in Adelaide. William Bragg, old man Bragg, was appointed to the chair of mathematics and experimental physics in Adelaide in 1885, which is extraordinary, at least insofar as he knew absolutely no physics, which he was quite happy to admit. He learned all the physics that he knew on the boat out of the book. But he made a show of it. He founded a very successful school of physics in Adelaide. William Bragg was born in Adelaide in 1890 and read mathematics at the University of Adelaide. The family went back to England, as was the fashion in those days, in 1909. William to the Cavendish Chair of Physics at Leeds, University of Leeds, and young Lawrence to Trinity College, Cambridge, where he was a research student. And on their summer holidays in Yorkshire in 1912, William Bragg showed Lawrence Bragg this image, which was sent to him as a preprint from Germany. It was the work of von Laue, and this showed the first known image of refraction from a crystal and the characteristic spots, which we'll see tell us everything about the underlying structure. Now, Laue made some mistakes. Laue assumed that these spots were actually due to fluorescence of X-rays from the crystal, and he kind of pushed the theory around in order to fit his preconceptions about what the structure was supposed to look like. And he got a reasonable job and he got physically plausible results, but it wasn't actually the correct structure of zinc blende, which is the mineral that was used to obtain the crystal structure. But it turns out that Lawrence Bragg had a number of lucky breaks. He realized that the signals in von Laue's images were caused by reflections, because he believed that electromagnetic radiation, and X-rays in particular, was a wave-like phenomenon, whereas his father strongly believed that it was particular bunches interacting with matter. And he said that the idea came to him while walking in the Backs in Cambridge, which is the meadowland to the back of King's College. Moreover, unlike a lot of my own students, Bragg attended all the seminars that were put on in Cambridge, and he attended a seminar that was given on mineralogy and crystallography. He learned a thing or two. He realized that there was more to crystallography than just cubes. There were hexagons and triclinic structures and all sorts of fancy stuff. So he became quite interested in this, and he realized that each of these characteristic structures of the Bravais lattices would have different interference patterns if he took his idea of reflection seriously. And so he said, well, what if zinc blende is not the simple cubic structure that von Laue assumed? What if it's some related structure? What if it's a face-centered cubic structure? And what if the spots are actually caused by X-ray reflections? He even understood, once he made that leap, the characteristic ellipsoidal shapes of the spots. So if you go back a bit, you can see that the spots aren't really spots at all, they're ellipsoidal. Bragg actually realized that this was a characteristic signature of the experiment itself, and a weak focusing effect that was caused by the geometry of the experiment and the crystals. And so what he did was he reanalyzed the original data and obtained the correct structure, and he didn't have any leftover reflections, and everything fitted into place. Hot on the heels of Bragg and Bragg were Moseley and Darwin. I talked about Moseley last year. He's a personal hero of mine. Moseley and Darwin worked together in Manchester with Rutherford to understand the nature of X-rays. This whole question about what were X-rays was still an open question in those days. Moseley learned how to generate X-rays by taking the train up to Leeds to see Bragg. He became an expert, probably the world authority in producing efficient X-ray sources, and together Moseley and Darwin published a number of papers, but one particularly influential paper about the reflection of X-rays by crystals. And although they didn't discover X-ray crystallography and they didn't really use it to determine structure, they were very influential in constructing spectrometers. So the bottom line is that Bragg's law relates the wavelength of the incident light, the incident angle relative to the planes of the crystal, and D, which is the separation between the planes of the crystal. By elementary wave analysis, Bragg showed that whenever the angle satisfied that condition, an integer multiple of the incident wavelength, then one could expect to see a bright reflection in the photographic film. And a diagram is shown at the bottom. So it cuts both ways. If you know the wavelength, you can determine D. And if you know D, you can determine the wavelength because it's a reciprocal relationship. And so once you've worked out by some means or other what the spacing in a particular crystal plane is, then you can actually tilt that crystal plane and actually pick out particular wavelengths. So it's actually used as a crystal grading monochromator, actually taking a polychromatic source of light and then pulling out a single wavelength. This is what Bragg diffraction looks like. It's a very dense series of dark spots. Dark spots mean high exposure on a photographic film. The hazy background is just a diffuse background that's caused by inelastic scattering, mainly. You don't have to have single crystals. You can, in fact, take a powder which is made by a crushed up crystal because each of the crystals will present at a random orientation to the incident direction of the wave. And some of the crystals will satisfy the Bragg condition and they'll produce spots. And if you have enough crystals and they're sufficiently randomly orientated, then what will happen is the X-rays will be thrown out in a cone, and each one of those cones is characteristic of a particular crystal spacing. And if you intercept those cones with a detector, which is typically a photographic plate, though these days it's actually a high-powered version of the thing in the corner of your pocket calculator. It's a charge-coupled device. You can collect the data of the scattered X-rays and actually reanalyze the structure. And this is a typical example of powder diffraction. You see these characteristic Dubuis-Scherer rings. This is the pattern for lanthanum hexaboride, which is a standard that's used for calibrating X-ray spectrometers. And this is what got Armstrong so upset. So on the left we have the structure of common salt, and these days we would quite happily say that this was an ionic structure consisting of positively charged sodium ions, which are the little purple dots, and negatively charged chlorine ions, which are the larger green dots. And they form this checkerboard pattern that so infuriated Armstrong. But it tells you nothing about how they're stuck together. The only thing that Bragg did, and people that followed him, was they determined where the atoms were. Not how they were stuck together, just where they were. So the structure of rock salt is this cubical lattice of alternating positive and negative charges. The diamond structure is this characteristic tetrahedral arrangement in which every carbon atom is attached to 4 other carbon atoms. And in fact, the whole argument about what holds stuff together was an open question well into the 30s, simply because the means had not yet really been devised to apply quantum mechanics to describing complex structures like molecules. It took the whole of the 1930s to develop simple models that came up with reasonable qualitative results. The first plausible account of chemical bonding was actually made by Pauling in 1939 and by Charles Coulson much later in the 1950s. So Armstrong was infuriated simply because he had a preconception about how it was supposed to be stuck together, not any real information because that came much, much later. So Bragg went on to determine the structures of common salt and diamond with his father, fluorspar, zinc blende, iron pyrites, calcite, all very simple structures. The solution of the diamond structure seemed to have the greatest impact, and is the one that William Bragg publicised and talked about in his Beckerian lecture. But it's worth bearing in mind, and it's certainly been relayed by people who were there at the time and by the recent biography, that X-ray structure and structural analysis is almost entirely the work of Lawrence Bragg, and it's Bragg's law apostrophe S, not Bragg's law S apostrophe. Father and son won the Nobel Prize for Physics in 1915. Which brings us to a simple discussion about diffraction physics. This is a schematic picture of an atom. And so what I'm going to attempt to do is to give you some insight into what happens when the X-rays hit the solid. So the red bit is the nucleus. It's the heavy center in the middle, and the electrons are much more mobile on the outside. And this represents an incoming wave, which is going to interact with the atom. And because an incoming electromagnetic wave is an oscillating electric field, it will actually push the electrons up and then down, and what it will produce is an oscillating dipole, and an accelerating dipole produces an electromagnetic field. And so if a plane wave comes in, it interacts with the atoms. Because the electron distribution is distorted upwards and then downwards because of the transverse electric field of the X-rays. It causes a dipole to form, which is then, when the electric field changes over, the electrons are re-accelerated back to the nucleus, and it gives off this characteristic spherical wave of radiation at the same wavelength as the incident wave, but now it's dispersed. And if I have an array of atoms, so if I have a number of atoms all lined up, and I have a plane wave interacting, then they all behave exactly the same. And each of them produces a spherical wave, and the spherical wavefronts propagate out through space, and at points where they intersect, one expects to see constructive interference between those wavefronts. And if a peak hits a trough, then what you expect to see is destructive interference, and the sum of those waves tends towards zero. And so having 4 atoms all producing electromagnetic waves doesn't just produce 4 times the pattern of the original one. What you have to take into account is the displacement between the origins of the spherical waves and the addition of the wavefronts as they propagate through space. Now, the scattering probability is given by the structure factor, which is the Fourier transform with electron density, which is a technical phrase, but suffices to say that the strength of the scattering, that is the probability of producing electromagnetic radiation at a particular angle, is actually determined by breaking the electron density down into its momentum components term by term, by integrating over e to the minus I q dot r. And because atoms are spherical, the probability of scattering through a particular angle, theta, is determined simply by the magnitude of q, which is the magnitude of the momentum which is transferred from the incident wave to the scattered wave, and the wavelength, and nothing else. And so you get this spherically expanding distribution for each atom. And if I have an electron distribution for a solid, which is made up of the electron distributions of the atoms, and in this case all the atoms are identical, then I just sum up the electron density at each point Rm, and I get the superposition of all the electron densities, and then I take the Fourier transform of all of that, and it has this rather simple form in which I can take out f of q, which is characteristic of one atom out the front, and the sum over all of those factors, e to the I q dot r, which gives me all the positional information about where the atoms are. And the intensity that I measure is actually the square, the complex square of that quantity. And a little more maths tells you that you only see a Bragg peak when the quantity q, which is the momentum transferred to the scattered X-ray, multiplied by the distance between 2 scattering atoms, is equal to an integer multiple of 2 pi. And this is essentially a restatement of Bragg's law. Now, this representation in terms of Fourier series was actually first suggested by William Bragg, by Lawrence Bragg's father, but it was taken up and developed by Lawrence Bragg, who developed what is now the routine method for structure analysis, because all protein crystallography and all the methods of structure determination are all really based on the Fourier transform. Amazingly, I discovered that Bragg did all this by hand. In determining the structure of dioxide, which is a compound involving magnesium and calcium, 2 silicons and 6 oxygens, which is not the most complicated thing on Earth, it required the calculation of 17,760 values of e to the I q dot r, which he added up laboriously by hand over the course of about a year, and got the right answer. Well, that's pretty good, because I'm pretty sure I couldn't. Now a trivial all of this is now a trivial calculation on electronic calculators, and I'm sure I could code up the structure determination of dioxide, and it would run like that on this rather antiquated laptop. And there's 2 things. One is the computer, and one is the algorithm for performing that summation. There's an algorithm which was only really published in 1965 called the fast Fourier transform algorithm, which allows you to sum up those points in logarithmic time, so n log n. So if I double the number of points, the amount of labor only goes up as 2 log 2. If you do it the way that Bragg did it, it goes up as the 4th power of the number of data points that you collect. He did it on a very crude grid and to low resolution, simply because human endurance simply couldn't possibly manage to do anything more. Now, as a way of illustrating this, I've come up with an analogy which I rather hope works. What I hadn't banked on was this large, baffling podium here, but we'll give it a go. What we have is an analogy, an acoustic analogy between the atomic centers which are producing the spherical waves and the production of sound. And so I've replaced the atoms, which are producing spherical waves, by these little speakers here. And if I turn it on, then they will, and I'll do that in a moment, it's a little ear splitting, it produces spherical waves coming out of each of these faces, and it's actually producing pressure waves which are separated by a distance lambda. And because Steve has very kindly set this up for me, and I thank Steve for setting up the experiment, on the little boxes here I can actually change the phase of the waves which are coming out of the boxes so that the pressure waves relative to one another are shifted either forwards or backwards by half a wavelength. So rather than every atom or every speaker behaving in exactly the same way, I can actually change the behavior of the speakers in terms of the relative behavior of these propagating waves by half a wavelength. I can change the wavelength by the tone generator. I can't do anything about the speed of propagation because that's the speed of sound, and that's about 314 meters per second, depending on the humidity and the temperature. And I can change the distance between the speakers, and the school budget wouldn't run to having an infinite number of speakers, but 6, as in my world, there's 1, 2, and there's an infinite number. 6 is a huge number. So we'll give it a go. This is 300 hertz, and I switched them all off. So I've got a 300 hertz signal being beamed out. I can switch the speakers selectively, so that turns on that one, and that turns on that one, and I'm not sure whether this is going to work, but they're separated by 0.8 of a meter. And I worked out that for this particular wavelength, there should be a distribution of intensity, probably maximum along this distance, this direction here, and it will become lower as you go in either direction. Now, it's a little hard to hear, and I didn't know exactly how this was going to work out, but I have the change in the phase. It does seem to me that you should hear a difference between those two. And that's because I can either have it so that the two signals are coming out in phase and constructively interfering at various points across the room, or I can actually change that one to have a positive phase and this one to a negative phase. And what it will do is it will change the position of the maximum points to a different place in the room. But exactly the same amount of power is coming out of each of these speakers. And if I just turn on one speaker, and I change the phase, then it should sound exactly the same. Much nodding of heads, excellent. But if I turn on this one, and I change the phase, and I swap between them, then you should be able to hear a noticeable difference in the intensity. And if we go for broke, and we turn them all on, and I put them all in phase, so all positive phase, then across this room there'll be a distribution of bright spots and dark spots, and if I change any one of these by the phase, then you should all be able to hear a significant difference in the sound, which is caused not by the intensity, but simply by the phase and the phenomenon of constructive and destructive interference. Now, it's a bit of a pity about this. And it's a bit of a borderline case, because the standard theory, and this is an example of a grating actually, the standard theory says that d sine theta, so if I'm standing here in the middle, and I look in this direction, d sine theta, d is the distance between the point sources, which is 0.8 of a meter. Sine theta is the sine of the angle between here and sweep across the room, should be an integer multiple of the wavelength. It turns out that for the particular wavelength that I chose, you do get a substantial effect, and we tried it earlier as we take a sound meter across, but I think it's because of this baffling effect here that you don't get the deluxe effect. It's probably best that you don't get the deluxe effect, because if you're in somewhere in the middle of the audience, then what you'll hear is not 6 times the intensity that you would hear from one speaker, but 36 times the intensity that you would hear from one speaker, and that is in no small measure why crystallography has been so successful. It's because crystals and crystallography act as amplifiers. The signal, which is scattered from each individual atom, is constructively reinforced from the signal from every other atom, and the intensity that you get doesn't depend on the number of atoms, it depends on the square of the number of atoms. And that's why Bragg spots are so very bright, and why it's so very dark everywhere else. I should turn off. Right, how am I doing for time? Right. Very briefly, quasi-crystals. Quasi-crystals are ordered, but they're not spatially periodic. So if we look at this crystal here, you can see that it has a 5-fold symmetry in the middle. It's constructed entirely from fat rhombuses and skinny rhombuses, grey ones and green ones. But it has no translational symmetry. You can see that you've got a 5-fold element in the middle, and it's surrounded by a sort of ring of grey-blue fat rhombuses, but there is no place anywhere else on that crystal where you get that full ring of fat rhombuses. Nevertheless, if I were to put an atom at the location of every intersection of the black lines, and take it to a synchrotron and construct the diffraction pattern, I would actually see Bragg diffraction from this particular structure, much to the surprise of people. In fact, this became a subject of intense research, certainly in the 1970s, and the pictures of Sir Roger Penrose, who was Rousable Professor, or is Rousable Professor of Mathematics at Oxford University. He spent a great deal of his time looking at these tilings, inspired actually by the work of Kepler. Kepler knew a lot about solid geometry, and one of this green object rotating around is one of Kepler's stellated solids. And Kepler knew that you could tile a 2-dimensional surface using pentagons if you filled in the missing region with pentagrams, 5-pointed stars. And Penrose took this idea and tried to work out the simplest possible way of producing a tiling which was complete in the sense that it had no gaps, but aperiodic in the sense that it never repeated itself. The simplest of all the Penrose tilings consists of 2 rhombus, or rhombi, of precisely the type I showed you earlier, and the ratio of the green rhombus to the grey rhombus is actually the golden ratio. It's 1 plus the square root of 5 over 2. And here is an example close to my heart of a tiling, an actual tiling, and many's the night I've been out on the tiles on a nice summer's night in Oxford, because that is the tiling on the bar of Wadham College, Oxford, and those marks on the ground are almost certainly beer stains, and I recorded that. Now, if you want to grab onto something about what these tilings are, certainly when I went to high school, we were learning about conic sections, and the idea is that circles and ellipses and parabolas and hyperbolae are sections through cones. Well, these Penrose tilings are themselves 2-dimensional surfaces through 5-dimensional objects. And it turns out very difficult to visualize, but that's how they're constructed mathematically. Quasi-crystals, crystals which have this property which occur in nature, formed by taking projections through higher dimensional lattices. And here is an example of an aperiodic solid, which is a 3-dimensional object which is taken by projecting through a 6-dimensional hypercube. These were discovered in 1982, as I said, by Daniel Schechtman, who obtained that diffraction pattern and was deeply alarmed by it, because every well-brought-up crystallographer knows that it's impossible to have a diffraction pattern that exhibits tenfold symmetry. It violates one of the fundamental rules of Bravais lattices and space groups. Tenfold symmetry in diffraction patterns violates what's known as the crystallographic restriction theorem for the Bravais lattices. And so I stopped him from publishing it. He sat on this, he said, well, I'm not going to publish this, everyone's just going to laugh at me, because everyone knows that tenfold symmetry is not allowed. And so he tried twinning, and it was two crystals at once, and finally he did a computer simulation to find out what sort of thing it was that produced this particular diffraction pattern, and the solution was one of these aperiodic tilings. There are about 100 known alloys, mainly involving aluminium, which have this property, and there's one known naturally occurring example of an aperiodic structure, which is icosahedrite, which is almost certainly meteoric in origin. And for this work, Schechtman won the Nobel Prize in 2011. So briefly, since time's getting away with us, I'll discuss where this is all leading. All of this is now leading, so this is the historical and traditional representation of crystallography. In the beginning there were minerals, then there was Bragg diffraction, then there was the solution of structures on the assumption of spatial periodicity. Then there was this small wrinkle in terms of aperiodic structures or quasi-periodic structures, which was led by Schechtman. But now the question is, well, where is it all going? And the answer really is a partnership between physics and biology and engineering to solve the big problems. This white paper, which was produced by the Massachusetts Institute of Technology, identified three main revolutions: cellular biology, genomics, and a convergence between the life sciences and physical sciences, high-speed computation, and large facilities, which would lead to the solution of frontier problems for the benefit of all. So revolution zero, of course, was Hooke's Micrographia, and I've discussed that last year and earlier in the talk, so I won't dwell on that. Other than to show again the beautiful pictures that Hooke drew, which captured the imagination and led to sort of a cult of the gentleman scientist and his interest in microscopy. Microscopes were very primitive things in 1665, and this is Hooke's original optical microscope. These days, microscopy involves multi-million-dollar devices, but still in laboratories, involving large computer installations and powerful lasers. But they're still optical, and they're just super-duper Hooke microscopes, really. But the coming storm is the molecular microscope, which is based around this 300 kilometer long accelerator facility in California, which is able to produce very intense X-ray light. And the hope is that one can produce a molecular microscope to look at biological samples with atomic resolution, but without making crystals. So revolution zero. The physicist Hero Feynman said there's plenty of room at the bottom, and Feynman made the statement that we always quote on biology: if you want to answer a question in biology, just look at the thing. What Feynman was basically saying is build a better microscope. And so the contribution of physics to biology has been, for hundreds of years, to build better microscopes. Feynman also, in the same lecture, opined that there was no fundamental limit to information, and that he foresaw the current trend towards quantum computation and information technologies based on quantum mechanics. So the molecular microscope would seem to be the logical outcome of Feynman's exhortation to build better microscopes for biology, and one imagines that Hooke would agree. Protein crystallography was driven by the discovery of DNA, and this is the famous photo 51, which captured the characteristic cross of a helical structure. On the right is Rosalind Franklin, who actually took the image and sadly died before she could even really be considered for the Nobel Prize. Photo 51 is probably one of the most important images in the whole of science. And what does it mean? The cross structure is a characteristic of a helix. And that's known because of the square of the Fourier transform of a helical structure is cross. The distance between the small dark spots that you can see tells you that that helix repeats itself every 34 angstroms, and the distance from the center of the image to the outside tells you that the distance between each of the rungs in the helix is 3.4 angstroms, which tells you that there are 10 rungs per spiral. On top of that, you include some chemical information and some biochemical information, which is known as Chagall's principle, which tells you that the amount of cytosine and guanine has to be identical, and the amount of thymine and adenine have to be identical. And so that puts a constraint on the kinds of molecules you're allowed to build that are 34 angstroms long, helical in structure, and have rungs which are 3.4 angstroms apart. And so these days you fire up a computer program, but in 1953, Crick and Watson fired up a soldering iron and produced models of those basic elements, or actually had the people in the workshop produce models of those basic elements. These hexagons and pentagons that you can see are actually old jam-tins, which have been soldered onto thick bits of wire. It's all held together with Bunsen burner stands, and it's all to scale, and they measured out the distances. They applied Chagall's principle about the matching of base pairs, and they discovered that it was actually two intertwined helices, each connected by the base pairs in this Meccano model. It's now in the centre, on the ground floor of the London Science Museum, even though it's just old Bunsen burner clamps and bits of wire. Applications of this, the structure of DNA, as we already said, and the structure of the influenza virus itself, which is used by the CSIRO to develop Relenza, which is pretty much the only effective treatment for avian flu. Nobel Prizes in protein crystallography, too small to read, but suffice it to say that there are a lot of them. And so all of the high points of chemistry and biology, which have occurred in the past 40 years or so, have all had a very strong element of crystallography in them, like the determination of DNA, the structure of hemoglobin and the globular proteins, the structure of vitamin B12, and insulin by Dorothy Hodgkin, who I met many years ago, the folding of proteins, the structure of photosynthetic centers, how natural products like leaves take light and produce energy. Crystal structure told us how that happens. The second revolution is genomics, which involves high-speed computing. Once physicists had really mastered the art of high-speed computing, it fed into biology in the 1970s and 80s. This is an image of the Cray 1S, which I'm sorry to say I used when I was a graduate student, which just says I'm getting old. And even worse than that, it's now on proud display also in the London Science Museum, next to the model of Crick and Watson's DNA. This is IBM having its little joke. This looks rather like the monolith out of 2001 on its side. This is the super duper IBM supercomputer, which is just around the corner actually in Grattan Street, and the Victorian Life Sciences Computational Initiative in the University of Melbourne is dedicated. It's the largest dedicated centre in the world solely for computational biology. And Revolution 3 is convergence, large-scale interdisciplinary programs, rather like the type that my centre is engaged in, taking the tools and expertise of fundamental physics and applying it to the life sciences, to utilise large international facilities, supercomputers, synchrotrons and free electron lasers, whatever it takes and whoever it takes to get the job done in an enterprise which is much more like particle physics than conventional biology. So these teams now involve certainly hundreds of people, and the teams which are involved in these collaborations are growing, simply because the size of the problems and the complexity of the problems is also growing. The most active area of crystallography, the newest development, is femtosecond nanocrystallography, which uses these free electron lasers. On the left, you can see a diffraction pattern which was gathered at LCLS in just outside San Francisco, and on the right is the structure of photosystem 1, produced by almost 1 million independent diffraction patterns collected by dropping individual crystals into femtosecond pulses of X-rays, collecting all the data, analysing the orientation of the crystal relative to the X-ray propagation distance, and then assembling all of that information to determine the crystal structure in precisely this way, that you take individual molecules or tiny crystals, drop them one by one into the path of femtosecond pulses. The pulse causes a diffraction, which is collected by a detector, and the molecule blows up. But it blows up after it's produced its signal, so it doesn't matter. Except to the biologists who cry, but it took us years to produce these samples, and you just want to blow it up. Guilty. So the object of the exercise is to turn a molecular structure, and what chemists and biologists mean by a structure is the thing on the left. It's a ball and stick model which tells us about the positions of the atoms, and on the right is what a diffraction pattern of a single molecule looks like. No Bragg spots. There is no periodicity in this structure, not even quasi-periodicity, and therefore there is no Bragg structure in this diffraction pattern. Now, it turns out that the solution of the mapping between these two things has much in common with the solution of Sudoku puzzles and also code breaking, though I don't propose to discuss that this evening, other than to say that if I have a certain amount of information about the thing on the left, which is the molecule, how big it is, for example, and what its chemical composition is, and if I have information on the right, which is the measured intensities, and I know, or I have a rule which maps structure to diffraction, which I do, which is the laws of electrodynamics, then if I constrain, or I find a self-consistent solution that satisfies those constraints, and the two are related by the mapping, then I can solve for the structure. And so in the case of the molecular structure problem, I have the molecule which has a certain size and a certain chemical composition. I have a diffraction pattern which has no periodic structure, and I have a mapping which is the mathematical propagation of light between the molecule and the detector plane. And if I can find the cursor, this is a simulation, there it is. This is a simulation of the reconstruction of the structure of bacteria rhodopsin from its diffraction pattern, from an initial assumption that all the electrons are uniformly distributed on a sphere. So I make no further assumptions about chemical bonds or what sort of bonds or anything like that. All I have is data, and I know that the molecule is smaller than a certain size. And if I start the simulation, I go back and forth between the detected plane, which has the diffraction information, and the object plane, which imposes the constraints about how big the molecule is. And within 500 iterations of going back and forth, I get what this is, in fact, an exact reconstruction of the crystal, of the structure of an individual molecule of bacteria rhodopsin, simply on the basis of diffraction theory, the propagation of light, and the imposition of some simple constraints, not very restrictive assumptions, about what the solution has to look like. So in summary, it's a bit late, sorry. In summary, crystallography has told us almost everything we know about the structure of molecules and materials and about how they're assembled. Protein crystallography determines the structures of macromolecules and informs the design of new pharmaceuticals. So this is where a lot of biological physics is going, and the university has indicated its interest in really pursuing this as a collaboration between our side of the university and the other side of the university, east and west. And interdisciplinary research is entering new territory, requiring only nanocrystals or possibly just single molecules, but large facilities, highly intense light sources, and femtosecond pulses, so we can capture that information before the molecule blows up. So as a parting thought, this is Max Perutz, who is the winner of the 1962 Nobel Prize with John Kendrew for determining the structure of hemoglobin. And this animation is an oscillation between the oxygenated and deoxygenated forms of hemoglobin, which is a tetramer, consists of 4 molecules interacting with one another. The business end of this molecule is that reddy purple structure in the top left-hand corner. It's actually an iron atom which is sitting in a planar molecule called a heme group, and the oxygen molecule comes in from the left. It attaches itself to the iron atom in the heme group. It causes the entire group to go upwards, and you can see that there's a 5-membered ring which comes out to meet it and to attach itself to the top of the ion group. That acts like a little tether which pulls at the molecule, which then causes the molecule next to it to deform, which then causes a strain to be transmitted into the next heme group, and the next heme group, and the next heme group. So if I can absorb one oxygen molecule into the group, I can absorb 4 oxygen molecules into the group. And it's that miracle dance, that cooperative behavior between those 4 molecules which act together in the tetramer form of hemoglobin, which allows us all to breathe here this evening. Because if it were not for that change in the conformation and the very particular way in which the molecule bends and flexes and allows more oxygen molecules to come in, and conversely allows oxygen molecules to leave the system and then to be distributed through your body, then we just wouldn't be here. And so this rather exquisite cooperation between absorption of oxygen molecules, steric factors which determine the selectivity of the molecule to oxygen, the cooperation between the molecules, and its functionality, excuse me, in biochemistry is all down. The fact that we know all of that is all being brought about because we can do crystallography. And that's why it's important. Now, Max Perutz observed to Bragg. The Bragg United C-piece knows 2 cultures. There's discussion in the old days, still going on, may even be a discussion that we might have in the University of Melbourne about the separation between the arts and the sciences. That the arts always seem to be more heavily favoured, that someone that could recite the works of Cicero was more highly favoured than someone who could recite the second law of thermodynamics, and C-piece decried this at great length, but noted that Bragg was not such a man. He was intelligent, sensitive, artistic, imaginative. He thought visually rather than purely mathematically, in terms of concrete models that could either be static like his structures or dynamic like the interaction between electromagnetic waves and structures, or like order-disorder transitions in complex materials. His artistic gifts surfaced in the delicate watercolours and in his limpid prose. So although Bragg is sometimes portrayed as being someone who just did crystallography, and crystallography is part of physics which is a little maligned these days as being too deeply rooted in the past. In fact, its influence on other sciences and the development of biology and biochemistry in particular is central. I would like to think that we understand respiration because we know the structure of hemoglobin. And we know the structure of hemoglobin ultimately because Lawrence Bragg gave us a means to see a world in a grain of sand. Thank you very much.
You talk about DNA, RNA. DNA, RNA carry message and information. What different this information by quantum information? Thank you.
Well, the information which is carried by biological systems is really a code that has a complex alphabet, but it's still essentially a classical code. So the code is really the base pairs which make up DNA and which signal form in reproduction. A quantum computer exploits the peculiar properties of quantum mechanics, and in particular the fact that quantum mechanical waves carry phase, rather like the waves that we discussed here. Okay.
Any other questions? Yes.
Quite so I'm going to be able to determine what characterises life from non-life, as a virus to maybe a nano, or the smallest possible living thing, and haven't got any sort of like structure that makes a difference. Laboratory experience.
My understanding is no. I'm a physicist and not a biologist, And also I think it's a somewhat philosophical question about when life starts and is a virus alive, for example. Viruses, although they reproduce, they require a host to reproduce, and usually the signature of life and not life is the ability to self-reproduce. A virus has to have a host to reproduce in, and it produces its chemical structure by piggybacking on another living system. So I believe that that is the conventional definition.
All right, we'll take just one more.
Do you foresee a future where resolving the structure of proteins is possible without crystallography or other techniques? Like maybe just being able to get a protein in solution and determine the structure?
Yeah, well, it comes down to two things, and this is a subject of debate with my colleagues, but that scheme I showed you about the individual molecules dropping into the path of an X-ray free electron laser. In principle, if you crank the act to 11 and you make the X-ray free electron laser as powerful as you possibly can, then there is a theoretical point at which you get enough signal to do a reconstruction in exactly the way that I illustrated. However, it's a competitive race between signal and damage. And it's a fairly fundamental result in quantum electrodynamics that the probability of ionization to the probability of scattering is approximately 10 to 1 at any of the wavelengths that we operate at. So while you're performing this experiment, all of the electrons which are doing all the scattering are being boiled off. And by my best calculation so far, I think it's just possible if you were able to if you're able to collect about 10 million individual molecular images with an intensity which is at the far end of the predicted intensity for the next free electron laser at Hamburg, I believe it's possible.
All right, and on that note,